All right, your book chooses to randomly drop into this conversation at this point percent composition. So before we can go any further, you need to stop and know right now what percent composition is. Percent composition is the percentage by mass of an element in a given compound. And in case you've forgotten from algebra class, the percentage of element X in a given compound would be the mass of X in the compound divided by the mass of the compound. And because it's a percentage, what do we always multiply by for a percentage? We always multiply by 100. So the percentage of element X in a compound is the mass of X in the compound divided by the mass of the compound times 100. In other words, part over whole times 100, just like algebra class. So if you're asked what is the percentage of calcium hydroxide, what is the percent composition of calcium hydroxide, you would need to know the mass of each element in the compound and then the total mass of the compound. So the first thing I would do is I'd figure out the total mass of the compound. And to do that, I'm going to assume that I have 1 mole. If I have 1 mole of calcium hydroxide, then I have 1 mole of calcium, and according to my periodic table, that 1 mole of calcium has a mass of 40.078 grams. Then I'm also going to have 2 moles of oxygen and 1 mole of calcium hydroxide, right? See my little 2 there? So 2 moles of oxygen, according to my periodic table. Each are going to have a mass of 15.994 grams. So my mass of oxygen would be oh, my calculator turned itself off. How rude. 2 times 15.9994, or 31.9988 grams of oxygen. And my 1 mole of calcium hydroxide would also contain 2 moles of hydrogen, each at 1.008 grams. So my total mass of hydrogen would be 2 times 2.016 grams hydrogen. So now I have the mass of each element inside 1 mole of the compound. So I need the total mass of 1 mole of the compound, so I'm going to add those numbers together. And that gives me 40.078 plus 31.998 plus 2.016, or 74.092 grams of calcium hydroxide in 1 mole of calcium hydroxide. So to get my percent composition, what have I done? Step 1, mass of everything, right? I figured out the mass of each element and I figured out the total mass. So to figure out my percents, I'm simply going to do some division here. My percent calcium in calcium hydroxide would be the mass of calcium divided by the mass of my compound times 100 equals 54.092% calcium. I can get my percent oxygen the same way. My percent oxygen in the compound would be the mass of oxygen in the compound, 31.9988 grams of oxygen, divided by 74.092 grams of calcium hydroxide times 100 equals 31.9988 divided by 74.092, and that gives me times 100 43.188% oxygen. And then I have two options to get my hydrogen. Percents have to add to 100, right? So I could do it that way. Or if I wanted to, I could complete the process, and I could say my percent hydrogen is equal to my mass of hydrogen. My mass of hydrogen divided by my mass of calcium hydroxide times 100. .72 1% hydrogen. And that's how you do percent composition. Exact same as you would have done it if I'd never opened my mouth, right? Percent composition is easy, life is hard. All right, now let's move on to a more in-depth discussion of how we want to look at compounds and look at the empirical formulas. All right, the section of this section is near and dear to my heart. We're going to talk about elemental analysis. And the first step along the lines of elemental analysis is to discuss empirical formulas. What is an empirical formula? An empirical formula tells the smallest whole number ratio of atoms in a compound, as opposed to the molecular formula, which tells the actual numbers of atoms in a compound. Huh? Let's take a look at a couple examples here. Sugar, sugar. Perhaps the easiest way to talk about empirical formulas and molecular formulas is to look at some sugars. I've got some, above is the formula for sucrose, table sugar. Then we've got glucose. Then let's take a look at ribose. What you'll notice is when we look at these three molecules have different molecular formulas. These molecular formulas tell you exactly how many carbons, how many hydrogens, and how many oxygens are in sucrose. These molecular formulas tell you how many carbons, hydrogens, and oxygens are in glucose. These molecular formulas tell you how many carbons, hydrogens, and oxygen are in ribose. Your molecular formula tells you how things actually exist. If you look at these sugars, you may notice that these sugars all contain carbon, hydrogen, and oxygen. Not only do they all contain carbon, hydrogen, and oxygen, but look at the ratio. 12 to 24 is 1 to 2. 6 to 12 is 1 to 2. 5 to 10 is 1 to 2. 24 to 12 is 2 to 1. 12 to 6 is 2 to 1. Hydrogen to oxygen is 10 to 5 is 2 to 1. What you'll notice is that all three of these compounds have a ratio of 1 carbon to every 2 hydrogens to every 1 oxygen. All have the same ratio. This ratio of the elements in a compound is referred to as the empirical formula. This 1 carbon, 2 hydrogens, 1 oxygen would be the empirical formula for all 3 of those compounds. They would all share a common empirical formula. The empirical formula tells the smallest whole number ratio of atoms in a given compound. In this case, the smallest ratio for all 3 of these compounds is the same. 1 carbon to 2 hydrogens to 1 oxygen. Several compounds can share an empirical formula. Now, there is a relationship between the empirical formula and the molecular formula. The molecular formula is always a whole number multiple of the empirical formula. Okay, I'm going to pause for just a second to let you write that down. The molecular formula is always a whole number multiple of the empirical formula. And for purposes, we're going to represent this whole number multiple with the lowercase letter n. All right. Going to clean that up here. Bye-bye. Mathematically, we can say that the molecular formula equals the empirical formula times n. For example, our sucrose's molecular formula is 12 times the empirical formula, right? We multiply 12 times 1, we get 12 there. We multiply 12 times 2, we get 24. 12 times 1, we get 12. This whole number n also has another curious relationship. It turns out that the value that you're multiplying by there, that 12, or your number n, that n is always equal to the ratio of the molecular mass to the mass of the empirical formula. And you know what? I have this typed out nice and neat on the next slide, so let's take a look. Before we do that, though, real quickly, write down Roman Empire. Write down Roman Empire. I hope everybody wrote down Roman Empire. First thing we need to do, all right, the multiple n, as we've been calling it, is equal to the molecular weight divided by the empirical formula weight. If we look at our example here, what's the molecular mass of C12, H24, O12? Well, we have to go to our periodic table. We've got 12 carbons at 12.011 grams per mole, plus 24 hydrogens at 1.008 grams per mole, By the way, if you don't have your periodic table out to do this lecture with me, pause me and get one ASAP, because we are going to be doing molar masses faster and more rapidly than you've ever thought possible in your entire life. So get that periodic table out and have it handy in front of you. All right, let's see. We've got 12 times 12.011 plus 24 times 1.008 plus 12 times 15.9994 equals 360.317 grams per mole. So that's my molecular mass, or my molecular weight. My empirical formula weight, well, my empirical formula I said was CH2O. So for its mass, it's simply going to be, well, it's simply going to be 12 from the carbon plus 2 times 1.008 from the hydrogen plus 1 oxygen at 15.9994. And that's going to give me 12.011 plus 1.008 plus 15.9994 equals 30.026. So that's the mass of the empirical formula, so I put that there. 30.026 grams per mole. Now I'm going to divide 360 divided by 30, and what do I get? Surprise, surprise, surprise. I get 12, which is what I expected. Because what is this n that we've been solving for? You're saying, good question, I was kind of wondering that. This ratio of molecular weight to empirical formula weight, or 12, provides me what I need to multiply my empirical formula by in order to get a given molecular formula. And we'll have a lot of fun with that handy concept here in a second. Now, let's take a look of how we determine what an element's empirical formula is in the laboratory. Let's expand upon this. All molecular formulas are whole number multiples of the empirical formula. For example, the molecular formula, N2O4, would have an empirical formula of NO2, right? Because I could divide both 2N4 by 2, and that would give me the empirical formula NO2. What can I multiply this empirical formula, NO2, by to get N2O4? I can multiply by, of course, the number 2. But where does that 2 come from? How in the laboratory can we figure out what that multiplier is? In other words, can we determine experimentally what this factor is that we're going to multiply our empirical formula by to get our molecular formula? As you already know from my previous example, that multiplying factor is always going to be equal to the molecular mass divided by the empirical formula mass. The empirical formula mass for nitrogen dioxide is 46.06 grams. The molecular formula for dinitrogen tetraoxide is 92.011 grams. So if I take my molecular mass, 92.1 grams, divide by my empirical formula mass, 46, I get the number 2 for my multiplying factor. Chemistry is easy, life is hard, yes? All right, let's see if you're following. Why don't you pause me real quickly and try this one yourself? All right, thank you for pausing me. If carbon, hydrogen, oxygen is the empirical formula for a compound, and the molecular mass of the compound is 150.1 grams, what is the compound's molecular formula? So the molecular formula is going to be equal to N times the formula for my empirical compound. We know that N is always equal to the mass of the molecular formula divided by the mass of the empirical formula. They've given us in the problem that the molecular mass is 150.1 grams. We need to solve ourselves for the mass of the empirical formula. We know that 1 mole of our empirical formula has 1 mole of carbon. We know it has 2 moles of hydrogen and 1 mole of oxygen. At 15.994 grams. Punch that into my calculator and I get 12.011 plus 2 times 1.008 plus 15.9994 gives me 30.026 grams per mole. So that's the mass of my empirical formula. So I've got 30.026 grams going into 150, and I get N equals 5. So the mass of my, the formula for my, my molecular formula, my molecular formula would be CH2O times 5, or C5H10O5 would be my molecular formula. Chemistry is easy, life is hard, yes? Why don't you write down Han, the Han Empire, H-A-N, Han. It's very easy in the laboratory to determine the molecular mass for a compound and its percent composition. With those pieces of information, we can actually figure out the empirical formula and the molecular formula. It's a simple 4-step process. First, you figure out, let's do it like this. Let's do it in the context of a problem. A colorless liquid has a composition of 84.1% carbon and 15.9% hydrogen by mass. Determine the empirical formula. Let's focus on that part of the problem right now. Let's go from percent composition to empirical formula. And let's do it step style here. I'm told that I have a compound that's 84.1% carbon and 15.9% hydrogen by mass. And I'm wanting to know the empirical formula. When going from percent composition to empirical formula, you're going to follow a couple easy steps. And I've got a color flow chart in the notes here for you. But the first thing you're going to do is you're going to, when you have percent composition, is step 1. Assume you have 100 grams of the compound. Why 100 grams? Because if you assume you have 100 grams of the compound, that means that you have 84.1 grams of carbon and 15.9 grams of hydrogen, right? If you assume you have 100 grams, then those percents can now be read in terms of grams. So that's step 1. We're going to assume we have 100 grams of carbon. We have 100 grams of the compound. Step 2. Calculate the moles of each element. So what we're going to do is we're going to take those masses that we just calculated and we're going to change them to moles. I know according to my periodic chart that 1 mole of carbon contains 12.011 grams of carbon. So I know that I have 84.1 divided by 12.011 grams of carbon. So I have 7 moles of carbon. Now I do the same for hydrogen. I know that 1 mole of hydrogen, according to my periodic chart, 1 mole of hydrogen has a mass of 1.008 grams. So that gives me 15.9 divided by 1.008. That gives me 15.774 moles of hydrogen. One thing you do not want to do when you're doing empirical formula, when you're figuring the empirical formula from percent composition, is don't cheat yourself when it comes to sig figs. It's always better to carry too many sig figs in your calculations than too few when you're doing empirical formula. So that finishes step 2. We've calculated the moles of each element. Now we want to do step 3. Calculate the mole ratio of the elements by dividing the smallest number of moles. Calculate the mole ratio of the elements by dividing the smallest number of moles into the other number of moles. So what's our smallest number of moles here? Our smallest number of moles is 7, right? We've got 7 moles, we have 15 moles. What's smaller? 7. So what I'm going to do is I'm going to figure my mole ratio dividing 7 into everything. So I've got 7.019 moles of carbon per mole of carbon. So I wind up with the obvious statement that 1 mole of carbon is how many moles that I have 1 mole of carbon for every 1 mole of carbon. Now I have 15.774 moles of hydrogen, and I'm going to divide by 7.019 moles of carbon. And when I do that, I get 2.25 moles of hydrogen for every 1 mole of carbon. Step 4. If needed, clear fractions. What do I mean, if needed, clear fractions? Well, let's look at the result of our step 3 here. Our step 3 told us that for every 2.25 moles of hydrogen I have 1 mole of carbon. That calculation tells me that the empirical formula for my compound here is 1 carbon to 2.25 hydrogens. Can you have 2.5 atoms of hydrogen? No, you can't have 2.25 atoms of hydrogen, right? If you wrote the formula for your compound like this, you'd be saying that for every 1 atom of carbon you have 2.25 atoms of hydrogen. And you can't do that because you can't have 1/4 of an atom. So we have to get rid of that fraction. How can you get rid of 1/4? And some of you are saying, where did that 1/4 come from? Remember your decimals. 0.25 is the same thing as 1/4. 0.33 is the same thing as 1/3. 0.5 is the same thing as 1/2. 0.66 is the same thing as 2/3. 0.75 is the same thing as 3/4, right? So if I have 0.25, I have to get rid of that 0.25 by multiplying through by 4, because you can't have 1/4 of an atom. So I'm multiplying through by 4 to clear my fraction. When I do that, I get an empirical formula of C4H 2.25 times 4 is 9. So I wind up with an empirical formula of C4H9. If you've done this correctly and worked the problem correctly, you won't be able to divide these numbers down here by anything other than 1 and come up with a whole number. And that's how you get to empirical formula from percent composition. All right, let's take this problem a step further. Remember what our original problem was. Our original problem had 2 parts to it. Before I give you that second part, though, why don't you write down another empire? Let's go for the Ottoman. Ottoman Empire is a good one. Write down Ottoman. Meanwhile, back at the original problem, a colorless liquid had a composition of 84.1% carbon and 15.9% hydrogen by mass. Determine the empirical formula. That's what we just did. C4H9 was what we determined our empirical formula to be. Now they ask us, assuming the molar mass of this compound is 114.2 grams, determine the molecular formula of this compound. Remember, the molecular formula for a compound is always equal to the empirical formula times a whole number n. So to determine the molecular formula for this compound, I need to know what whole number n I can multiply my 4 and my 9 by. And we also said that this multiple that we multiply by is always equal to the ratio of the mass of the molecular formula divided by the mass of the empirical formula. They give us in the problem, and they usually will in the homework, the molecular mass. 14.2 grams per mole. We just need to figure out the mass of the empirical formula. Well, that's easy enough. Our empirical formula is C4H9. So if I have, why do I keep writing the letter G today? If I have 1 mole of my empirical formula, that means I have 4 moles of carbon at 12.011 grams each, and 9 moles of hydrogen at 1.008 grams each. So that gives me 4 times 12.011 plus 9 times 1.008, or 57.116 grams per mole. So now I have the mass of my empirical formula, and I can solve for N. So N would be 114.2 grams. Where did that 14.2 grams come from? Mount Sinai. No, it came from an experimentally determined quantity in the lab, right? 14.26 grams, there in the problem, divided by the empirical mass that we calculated, 57.116. And we divide 57.116 into 114, and we wind up with 2. So our multiplier is 2. So N equals 2. So we're going to multiply our subscripts here by 2. So that means my molecular formula would be 2 times C4H9. And what is it with the... That's what I get for watching Sesame Street in the morning. Multiplying by 2 gives me C8H18. Ta-da! And that would be my molecular formula. Deep breath. This really boiled down to 5 easy steps. Much easier steps than were used to found the Roman Empire, which I'm sure everybody has written down. Your steps are, when you're given the percent mass of an element, use molar masses to convert to moles of the element after you assume 100 grams. Go from moles of elements to mole ratios by dividing by the lowest number of moles. Once you have the mole ratios of the elements, you now have your empirical formula. And once you have your empirical formula, you can find your subscripts, or your molecular formula, by finding your multiplying factor N, which is always the molecular formula mass divided by the empirical formula mass. Let's work another example. All right, let's take a look at another example. Ascorbic acid contains 0.92% carbon by mass, 4.58% hydrogen by mass, and 54.5% oxygen by mass. What is the empirical formula of ascorbic acid? So we've got percent composition, and we need to go to empirical formula. So we're going to follow our easy steps here. Step 1, assume 100 grams. So if we're going to assume that we have 100 grams, that means we'd have 40.92 grams of carbon, 4.58 grams of hydrogen, and 54.50 grams of oxygen. Now in step 2, we're going to calculate the moles. So we're going to calculate the number of moles of each of these that we have. According to my periodic chart, there are 12.011 grams of carbon in 1 mole of carbon. 1 mole of hydrogen contains 1.008 grams of hydrogen, and 1 mole of oxygen contains 15.9994 grams of oxygen. And where did these numbers come from? They just came from the periodic table, right? All right, so now let's do some calculations here. 40.92 divided by 12.011 equals 3.406 that's a 9 moles of carbon. Now our hydrogen, 4.58 grams divided by 1.008. Whoops, punched into my calculator. 4.58 divided by 1.008. There we go. 4.5436 moles of hydrogen in our 100 grams of sample. Then 54.5 divided by 15.9994 is 3.4064 moles of oxygen. So now we've got our moles of each item. So now we're looking at step 3. Calculate the mole ratio. All right, so I'm going to do step 3 now, calculate the mole ratio by dividing the smallest number of moles into the others. So my smallest number of moles here appears to be tied, right? I have 3.406 moles of carbon, 3.406 moles of oxygen. Oxygen's a little bit lower. So we'll make oxygen the winner here. So I'm dividing 3.406 moles of carbon by 3.4064 moles of oxygen. And I get 1 mole of carbon for every 1 mole of oxygen I have. Now I do the same for my hydrogen. 4.5436 moles of hydrogen divided by 3.4064 moles of oxygen equals 1.33 moles of hydrogen for every 1 mole of oxygen, and 3.34064 moles oxygen is 1 mole of oxygen, of course, for every 1 mole of oxygen. All right, so now we have our mole ratios. And what does those moles ratios tell us? They tell us, whoops, I need some more space here, just a second. Okay. Extend my paper here. Haha. All right. So now we know that for every 1 mole of carbon, we have 1.33, well, for every 1 mole of oxygen, we have 1 carbon and 1.33 moles of hydrogen. Another way to think about this is for every 1 mole of for every 1 atom of oxygen I have 1.33 moles of hydrogen. Can I have 0.33 moles of hydrogen? No. Now, hopefully, you recognize 1.33 is one of those magic numbers That's really saying you have 1 1/3 atoms of hydrogen. So how am I going to get rid of that third? Multiply through by 3, right? So this is our step 4. Clear any fractions. In this case, to clear my fractions, I'm going to have to multiply by 3 because I have a third there. So that gives me 3 carbons, 4 hydrogens, and 3 oxygens. Where did the 4 hydrogens come from? Because 1 1/3 times 3 is 4, right? So my empirical formula would be C3H4O3. Chemistry's easy, life is hard. As long as you follow the 4 steps, you'll be fine. Assume 100 grams. Calculate the number of moles. Divide the least number of moles into the other 2. Resolve any fractions. Now, both examples that I've worked for you have had fractions. Most of the ones you have on the homework actually won't have fractions. I'm working the hardest examples here. Let's keep going. All right, here's another example. Why don't you try it yourself real quickly? Pause me. Please, I really think it'll benefit you if you'll pause me. Some of you are saying, I think it would benefit me a lot more if I could just shut you up and turn you off. I heard that. But you can't, so pause me, work it. All right, did you pause me? Tell me you paused me like a dog. All right? Pause, dogs, get it buried. A compound is found to consist of carbon, hydrogen, and oxygen by mass of 40%, 6.7%, and 53% respectively. The compound's molecular mass was 90.08 AMU. What is the molecular formula for the compound? In order to get the molecular formula, we first are going to get the empirical formula. So we're going to do this in 3 steps. Solve for the empirical formula using our 4-step method. And once we have that empirical formula, we're going to solve for the multiplier n. So let's solve for the empirical formula first. So step 1, we're going to assume 100 grams, meaning that we're starting off with 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. Step 2, calculate our moles. Once again, I go to my periodic chart, and I know that 1 mole of carbon is 12.011 grams of carbon. I know 1 mole of hydrogen is 1.008 grams of hydrogen, and I know 1 mole of oxygen is 15.9994 grams of oxygen. So I come up here and I get 40 divided by 12.011 is 3.33 moles of carbon. Then 6.7 divided by 1.008 is 6.65 moles of hydrogen, and then 53.3 divided by 15.9994 grams of oxygen says 3.33 moles of oxygen. So now we're going to do step 3. Divide the lowest number of moles into the others. In this case, my lowest number of moles appears to be my carbon or my oxygen. Let's just switch things up this time and make it the carbon. 3.33 moles of carbon per mole of carbon is 1 mole of carbon for 1 mole of carbon, duh. 6.6 moles of hydrogen per 3.3 moles of carbon gives me 2 moles of hydrogen per 1 mole of carbon. 3.33 moles of oxygen divided by 3.3 moles of carbon gives me 1 mole of oxygen per 1 mole of carbon. That makes my empirical formula 1 carbon, 2 hydrogens, 1 oxygen. So that's my empirical formula. Notice that this time there's no fractions, right? I have an even number 2, so I have no fractions, so I don't really need to worry about multiplying by anything to clear fractions. No fractions, so no step 4. So we have our empirical formula now. Now we want to get that molecular formula. So we're actually going to roll in those other things we were doing. We know, because of the problem, that the compound's molecular mass is 90.908. To get from empirical formula, the molecular formula, remember, is equal to a multiplier times the empirical formula. And this multiplier is always equal to the molecular mass divided by the mass of the empirical formula. So what we need to do here is we need to calculate, well, they gave us that the molecular mass here is 90.098 AMU. So now we just need to calculate the empirical mass. We come over here and we say 1 molecule of this has 1 atom of carbon. 1 atom of carbon is 12.011 AMU. It has 2 atoms of hydrogen at 1.0018 each for a total of 2.016 AMU, and 1 atom of oxygen at 15.9994 AMU. So we add that together and we get 12.011 plus 2.016 plus 15.9994 gives us an empirical mass of 30.026. So that's the mass of the empirical formula. And this is how we get our multiplier. And wow, that multiplier is going to be a nice even 3. So our molecular formula is equal to 3 times our empirical formula. So our molecular formula would be C3H6O3. Chemistry's easy, life is hard. Why don't you write down, what empire shall we look at next? Why don't you write down the Persian Empire? That's a good one. Write down the Persian Empire. All right, let's take a quick look at some combustion analysis. What is combustion analysis? Well, combustion analysis is exactly what it sounds like. In combustion analysis, you analyze the content of a substance by setting it on fire and collecting the gases that come off. Now, combustion analysis is really easy to do for carbon, hydrogen, oxygen. I worked with coal for a lot, so I did it with sulfur and nitrogen as well. And basically what you have is you have a small sample, and that sample will contain carbon, hydrogen, and oxygen. You'll place that small sample into a furnace, and it's important that you realize that you know the mass of this sample. You'll place this sample in a furnace, and you'll actually set it on fire. That fire, of course, is going to produce gases. You set a carbohydrate on fire. And you're going to get two gases out. You're going to get carbon dioxide, and you're going to get water vapor. All right, you've got that water vapor. That should be a G there. Coming out of your combustion. So you've produced combustion, and you've got a mixture of carbon dioxide and water coming out. It comes out of the combustion chamber and into a collection chamber. That collection chamber will usually consist of a series of glass tubes, kind of U-shaped. And in the first glass tube, you'll have something that's really attracted to water. Usually, calcium chloride is usually pretty used. It has a high affinity for water molecules. So you have this tube with calcium chloride in it. You'll know the mass of this tube and the calcium chloride before you set your gas on fire. The water will have such a high affinity for the calcium chloride that as the gas passes through the calcium chloride, the water will wind up staying behind, and only the carbon dioxide will wind up leaving. The difference in mass of this tube here before you set it on fire, before you set your sample on fire compared to what you had afterwards will be how you'll get your mass of water. Then your flue gas enters. Or if your flue gas, I'm sorry, you can tell I'm a coal chemist. Then your combustion gas enters another tube, and in this other tube, you'll usually have a strong base. Potassium hydroxide is a common one. Once again, you'll know the weight of this potassium hydroxide before you set the sample on fire. The gas passes through it, and all the carbon dioxide will wind up being trapped in that potassium hydroxide. So if you weigh the potassium hydroxide before and after setting your sample on fire, you can get your mass of carbon dioxide produced. So you can see it's really easy using a pretty basic instrument. I mean, you could jury rig one of these things very, very easily to calculate the amount of water and carbon dioxide produced from combusting a sample. We have to, however, look at the reaction. Here's what causes people a little bit of issues when it comes to combustion analysis. It's the stoichiometry involved in that equation. As a matter of fact, let me copy this reaction over a little bit neater. So we can talk about the problem. We know that when we set a sample on fire, that all the carbon and carbon dioxide that we collected came from the sample. So if I produce X moles of carbon dioxide, then I had X moles of carbon in my initial sample. Hydrogen's a little bit more difficult. It takes 2 hydrogens for a molecule of water. So if I have Y moles of water over here, then I actually have Y divided by 2 moles of water being produced. But once again, I can say with a great deal of assurity that any hydrogen in my water came from my sample. The problem comes from oxygen, because to set things on fire, what are we adding? By definition, setting something on fire is the addition of oxygen to it. So when I look at this carbon dioxide and I look at this water, the question is, is the oxygen from the sample or is it from the air? The hard answer is both. So the question becomes, in combustion analysis, how do we get our quantity of oxygen? Let me quickly summarize before I move forward. And I'm going to make my Z a little bit funky here, European style, just so people don't confuse it. with the O2, and that's a 2 for my oxygen. When performing combustion analysis, the amount of carbon is determined by the amount of carbon dioxide. The amount of carbon is determined by the amount of carbon dioxide produced. For every 1 carbon dioxide produced, the sample contained 1 carbon. The amount of hydrogen is determined by the amount of water. For every 1 water molecule collected, the sample contained 2 hydrogen. And that will cause people trouble on an exam, right? Ratio of 1 to 2 there. What about oxygen? Oxygen in our sample here, in our carbon dioxide and our water, can come from either the sample itself or from the oxygen we're adding in order to burn the product. Therefore, to get the amount of oxygen, what we have to do the amount of oxygen in a sample is obtained by calculating the mass of carbon in the sample using carbon dioxide to calculating the mass of hydrogen in the sample using water, and then taking the initial mass of the sample, subtracting the mass of carbon and subtracting the mass of hydrogen, and that winds up giving you the mass of oxygen in the initial sample. Once you have that mass of carbon, hydrogen, and oxygen, carbon analysis is just a basic, combustion analysis is just a basic empirical formula problem. Let's take a look at an example. All right, let's take a look at an example of combustion analysis. The substance responsible for bad smells is analyzed by combustion analysis. 0.45 grams of the sample gives 0.148 grams of water and 1.023 grams of carbon dioxide. What is the empirical formula of caproic acid? If the molecular weight of caproic acid is 1.126, what is the molecular formula? So what's our plan of attack here? our plan of attack kind of goes like this. 1, we're going to determine moles of carbon in our sample from carbon dioxide. We're also going to determine the moles of hydrogen from the mass of water. Once we have those, we're going to determine our moles of oxygen. And our moles of oxygen is going to be determined by taking the mass of the sample and subtracting the mass of carbon and the mass of hydrogen. And we're going to have to calculate both of those using the results from 1 and the results from step 1 and the results from step 2. Then we're going to do the normal steps for an empirical formula. We're going to do the mole ratios, dividing the lowest number of moles into the other two. All right, so that's our game plan. Let's take a look. Even though I've talked a while about this, this really isn't anything new. It's just a small twist on what we've been doing. And there are only 2 things to watch out for. Watching out for the fact that the hydrogen in water is a 2-to-1 ratio, and then the subtraction step. Those are the only 2 twists we have compared to what we've been doing previously. So let's actually work it now. All right, we have in our sample, step 1, let's determine our amount of carbon dioxide. So let's do our moles of carbon now. We have 1.023 grams of carbon dioxide. We want to figure out how many moles of carbon we have. So we do some math, and we go to our periodic table, and we say that 1 mole of carbon dioxide is equal to 12.011 grams of carbon plus 2 times 15.994 grams of oxygen, or 44.0098 grams of carbon dioxide. All right. And then we know that for every 1 mole of carbon dioxide I produce 1 mole of carbon. So I multiply everything on top, divide through by everything on the bottom, and I find out my sample contains 0.0 moles of carbon. All right, so now we have our moles of carbon. Check. Now we want to figure out our moles of hydrogen. So we're going to repeat the process, but this time we're going to start off with our water. I have 0.148 grams of water. I know that 1 mole of water is 18 something here. Let me actually do the math here. 1.008 times 2 plus 15.9994, 18.0154 grams of water. Two moles of, well, shoot, now I'm getting my moles ratios wrong here. I don't want moles of water, and this is the one that will get you messed up, and I see more people lose points on the exam for this problem than anything else. I know that 1 mole of water contains 2 moles of hydrogen. So I multiply everything on top, divide through by everything on the bottom, and I wind up with 0.0464, carry one more sig fig here. Actually, well, 3 sig figs carry 2 insignificant figures forward, moles of hydrogen. Those are the easy calculations. Now we have to do our moles of oxygen. So let's do our moles of oxygen. To get our moles of oxygen, we have to determine our mass of oxygen. And our mass of oxygen is equal to the sample mass, which they gave us here in the problem as, where did they give it to us in the problem? Here it is. Our sample mass, that 0.45 grams of sample, minus the mass of carbon, minus the mass of hydrogen. So we actually have to solve for our mass of carbon and our mass of hydrogen. So let's do that. Our mass of carbon is going to be equal to our moles of carbon from step 1 times the molar mass of carbon. And we know 1 mole of carbon contains 12.011 grams of carbon. So let's do it. And we get mass of carbon 0.023245 moles of carbon times 12.011 grams of carbon per 1 mole of carbon equals So that gives me my mass of carbon. Now I'm going to do the same thing again for my hydrogen. My mass of hydrogen, of course, is going to be equal to my moles of hydrogen from step 2 times 1.008 grams of hydrogen per 1 mole of hydrogen. So I have 0.046405 moles of hydrogen times 1.008 grams of hydrogen. And that gives me 0.046405 times 1.008 equals 0.04678 grams of hydrogen. So now I have my mass of hydrogen, I have my mass of carbon. So now I can get my mass of oxygen, which is what we started this thing for. So my mass of oxygen is equal to the mass of my sample from the problem, right? 0.450 grams of sample minus the mass of carbon in the sample minus my mass of hydrogen. And that gives me a mass of oxygen of 0.1241 grams of oxygen in my sample. That's only half the battle though, right? Because I don't want mass of oxygen, I want moles of oxygen. So once I have my mass of oxygen, how do I get my moles of oxygen? Well, I know that 1 mole of oxygen is, and let me change colors here just to signify that we're going through a different step. One mole of oxygen is 15.9994 grams of oxygen, and that gives me my moles of oxygen as 0.00757 moles of oxygen. So now I have my moles of oxygen. So let's clean this up just a little bit here. To make this a little bit more organized, we now have our moles of carbon, our moles of hydrogen, and our moles of oxygen. Let me provide us with a new sheet of paper here to work on. Virtual paper here. Alright, so in step 1, we have our moles of carbon. So we have our moles of carbon now. Then in step 2, we got our moles of hydrogen. And we said it was equal to 0.046405 moles of hydrogen. And then just recently in step 3 here, we got our moles of oxygen. And we said our moles of oxygen was 0.007757 moles of oxygen. So we may have our moles of carbon, hydrogen, and oxygen. Now that we have that, we're able to do our 4th step, which is to proceed to calculate our empirical formula as normal. So to do that, I'm going to take my lowest number of moles and divide it into my others. My lowest number of moles is my moles of oxygen. So I'm going to divide that into each of the others. So I've got all right, and that gives me, whoops, all right, just a second, I'm going to pause while I do some calculations here. All right. That gives me 3 moles of carbon for every 1 mole of oxygen. And here it gives me 0.046405 divided by 0.007757. 6 moles of hydrogen for every 1 mole of oxygen. And it also gives me 1 mole of oxygen for every 1 mole of oxygen. So my empirical formula would therefore have to be trying to find a blank space to write with, 3 carbons, 6 hydrogens to 1 oxygen. And that would be my empirical formula. All right, but the problem wanted more than just the empirical formula. That's just half the battle here. All right, so we have an empirical formula of C3H6O, and they want to know the molecular formula if the molecular weight is 1.16. And we always know what we're doing there is we need to solve for our multiplier, right? Our empirical formula times a multiplier n will give us our molecular formula. And remember, we've met m before. N is that ratio of molecular mass divided by the mass of the empirical formula. So we need to calculate the mass of our empirical formula. So that's 3 carbons, 6 hydrogens, and 1 oxygen. So that gives us a mass of our empirical formula of 3 times 12.011 plus 6 times 1.008 plus 15.9994 equals 58.0, and I've totally lost sig figs here, 58 grams per mole. So now to get our multiplier n, we take the molecular mass given to us in the problem, 16.2 grams per mole, divide by the mass of the empirical formula, and I don't even need to reach for my calculator for this one, you wind up with 2. So 2 is our multiplier. So our molecular mass would be C6H12O2, and I can't write 2. O2. Chemistry's easy, life is hard. Some of the problems are long. If you just follow the steps and think things through, it won't be too bad. Nothing like trying to build the British Empire. Why don't you write down British Empire? That's it. Beat.